Now we can delete all this stuff. And we're going to start as actually not string IE numerator, because we do need the IE numerator to start to like insert a timer. I will show you how to do that in a second. So now we're going to say while q.count. So if you recall from the BFS video, now we need to implement basically a BFS. So we have until our queue is not empty, we need to iterate through the queue. So now we'll say var node, we get our first node in the first node of the queue. If the node is not my destination node, so I do want to check that we're not in the start or the end position before assigning the explored cell material, because now we want to check actually checking if the cell should be explored. Okay, so basically I need to say nodes start position.x and start position.y, and our node is not nodes destination position.x and destination position.y. So if our node is not that, then we do want to assign the new material to the cell. So we basically do the same thing of before. We get the mesh renderer. Okay, material, and we assign it to explored cell. We don't want the start node and the end node colored of explored, because we want to see which is the start node and which is the end node. That's basically why we don't want to mark them as explored. Now we need to iterate through all the neighbors of the pixel. So how do we do that? We actually use a for each again, vector to int of neighbor. Okay, now we need to check that our neighbors are available nodes. So we do want to check if we are not in the bounds, because if we are in the bounds, maybe some node won't be available. So maybe some neighbors will not be available. So we do that with a huge if. Actually, this will be not clean code, so please be sure to refactor this code if you want to release the application. I'm just showing you this way because I guess it's easier to understand, but while you will reread this code, it could be tougher. So be sure to understand this and then refactor the code. We're going to check if the node current position.x plus neighbor.x is, sorry, not different, but is less than nodes.count. And then we're going to check, we're going down, node.current position x plus neighbor.x is greater or equal than 0. Basically, we're checking that we're not in the x bound, so we should be less than a row length and but greater than the first value, because otherwise we cannot take the first or because basically, so if we add 1, because in this way we're checking that if we are greater than 0 or less than count, then we're not in the bounds of the matrix. Actually, I'll speed through these in the video because it's not interesting to see all these conditions. Okay, after these conditions are implemented, we're going to explain why we have these conditions. So basically, we're checking that we are not in the x bounds. So basically, adding our neighbor x, for example, this doesn't get ourselves out of bounds or below the bounds in the X or in the Y. And then we just basically check that we are not in a wall node, so we're not exploring a wall node. That's the best way to check that we are not going out of bounds. So now we just say new node. I'm calling it this way. Maybe it's not the best naming, so you can choose another name. I suggest you to do so. Then I'm just basically getting the position of the current node. So node dot current position dot x and node dot current position dot y. And we need to add obviously our neighbor position, our neighbor offset, sorry, not position. That is an offset. Okay. And from here, we need to check that this node is not visited. How do we do so? We are basically new node dot visited. So if the new node is not visited, actually I missed one of these. If this is not visited, then we say q.add. We add the node to our q data structure. So we add the new node. Sorry, we add the new node. Okay. And then we say if the new node. Now we are checking that the current node is not the source node or the end node, because we don't want to mark the node with the new material that will be the visited material, because now we want to mark the new node as the next node to be explored. How do we do that? Well, basically we set it to in queue cell. So that means in queue means that it is in the queue data structure and we need to visit it, but it's not the current node that is being visited. So we just basically saying with the in queue cell material, we're just basically saying that this node will be visited soon. So we need to check the new node is not, as we said, there basically. So we can copy that and be sure to rename it to new node instead of a node. If it's not our start or end node, then we just say new node dot cell dot get component, as we did for all the other mesh renderer dot material equals in queue cell. Okay, so we're marking it with our in queue material, and now we need to set it to new node dot visited is equals to true, obviously, because we are visiting it right now. So no, sorry, we're not visiting it right now, but we will visit it later, so the node is in the queue. Now what we need to do after the for each is computing. Well, after we did that, we need to go under the if and then compute the new distance that this new node has from our current node, so the node that we're currently visiting. So we're just basically saying float distance. Let's call it distance. It's fine. We may add a comment. It's not a good practice, but now this is explanatory. Okay, we just say node dot distance plus Euclidean distance that stands between the new node and the node. We're going to implement this function in a second. And so we create the method. So the Euclidean distance will be the formula that I explained before. So we return the mathf.sqrt. Sorry for my typos. Mathf.pow. how did I call new node and node? Okay, so the power of new. Actually, let me rename this to x and x prime, as we said in the example. So power of x minus x prime plus mathf dot power of, yeah, I'm sorry. Let's call this node I and this node j for the sake of simplicity. Actually, I forgot that we were working with nodes. So I dot current position dot x and j dot current position dot y, sorry, dot x, and then we need to specify the power exponent. So I dot current position dot y minus j dot current position dot y, and then we'll specify the exponent. So that's basically the Euclidean distance function.